I'm Joel Jakubovic from the University of Kent, and this Onward essay was about building programming systems that have this nice property of self-sustainability. And that's the topic of my PhD research, which is being supervised by Thomas Petracek. I thought it'd be best to begin by showing you the system that I've been working on, which is called BootstrapLab. So I will attempt to transition to my browser here. Well, it's okay in this room. I assume it's okay remotely as well. So yeah, this is my prototype BootstrapLab. It is a web application running in the web browser, mainly using JavaScript as the implementation technology. And yeah, there are 3 columns here. The rightmost one is the browser developer tools, because you need to take advantage of whatever nice features you've got from your platform for developing a self-sustainable system. And because I'm familiar with the web platform, I'm productive in it and with JavaScript. And so it makes sense for me to take advantage of the tools that it provides. So I consider the developer tools and the JavaScript console down here as kind of part of the interface of the system while it's being developed. However, once it eventually achieves a self-sustainable state, this should be a throwaway. I shouldn't need this anymore, so I'd be able to hide this. The middle column is a view of the state present in the system. Is there a way I can move this? Ah, yes, there is. So this shows the state that's...
Could you maybe explain what you mean by self-sustainable? Is it the project sustains itself, or is it the software feature?
I will... a self-sustainable system is one where you can change how it works by working within it instead of having to go outside it. But I will explain that after I've shown this. So the middle column shows the state present in the system, and it's all based on key value dictionaries, just like the JavaScript that it's built on top of. And there are some interesting parts of this. So there are low-level machine instructions that also live in key value dictionaries rather than as binary things, because it makes sense to use the kind of natural state ontology in the browser platform and JavaScript. So it's got primitive machine instructions, and it's also got a high-level Lisp-based language, but because it's in a substrate that's based on dictionaries or maps, I call it MASP. So this is what the factorial function looks like in the kind of cumbersome tree view version of this MASP code. And the most interesting part of the state is probably the scene subtree. So this is a special part of the state where data structures in here, if you have a special property like text, then it will display some graphics in this window. And this is kind of the BootstrapLab proper. This is built, these graphics are running in Three.js, and that means that we have a lot more freedom to display whatever sorts of things we want compared to this HTML view of the state. So again, these 2 columns on the right, the HTML view and the browser developer tools, they are part of the temporary throwaway infrastructure of the system. So once the destiny of this system is for this left-hand column to kind of occupy the whole space and for that to be the interface that you work with. But until we get to the point where we can comfortably work in here, we take advantage of little things that we build along the way. So one limitation of the HTML view here is that it's just a viewer. I can't edit anything in it. But over here, I actually implemented a little state editor. So it's not just a viewer. You can also edit state. So for example, if I navigate into the scene subtree, go down to the data structure that describes this blue rectangle, then I see a color here, and I can edit this to be like green. And so that is connected there.
And you have this similar.
Power cable?
Yes. Thank you. Sorry.
It's okay. So that's directly connected to the. Yeah, so this part of the state controls the appearance of this shape. That's kind of a straightforward thing that you can do in the browser developer tools, like in the DOM inspector, you can change some hex string and get something to be a different color, right? But there is something else that we can do that is quite unique. It's not something you could do in an ordinary system. So this tree editor is composed of these little text boxes, and those are graphical elements that are displaying as they are because they occupy part of the state in the scene subtree. So in particular, this bit at the top that says root, that is a text box that has a data structure here, which is controlling it. And in particular, I can just change this to like root beer. And then that will also update. So the interface, I just used the interface to change itself in a kind of trivial way. But it's being able to, the fact that you're able to do something like that is a sign of a connectedness of everything that is important and hints at self-sustainability, which I'll go into in a bit. Okay. So the first thing to reiterate about BootstrapLab is that it cannot be described as a programming language. Instead, it's a interactive programming system. This picture summarizes this situation really. A programming system is a language plus everything else in the environment that it actually lives in. And the other salient thing about BootstrapLab, the raison d'etre of its existence, is that I'm evolving it towards a state of self-sustainability, where you'll be able to change how anything works using the running system itself. So the important parts of this are that you can make any changes, no matter how low level or deep changes that you want to make, you can make them using the system itself. There's no need to drop down out of your system into the deep dark world of C++ or something. You can make those changes taking full advantage of whatever fancy features happen to exist in your system. And just as important as that is that you're able to change the running system. So this means there's no need to destroy the world, recompile it, and start up a new one. I picked up the idea of self-sustainability from this paper, which describes a new way to design programming environments called a cola. And a cola is somehow implemented in itself. This means that everything, including the deep internals of the system, is up for grabs for you to change as a user of it. The paper puts it this way: the implementation language and abstractions of the system are precisely the language and abstractions that the system implements. And this ensures that everything can be modified, even the deepest behavior, on the fly. The go-to examples of programming systems that have this property of self-sustainability are always Lisp and Smalltalk. I personally feel that our de facto standard programming environment, namely Unix, also largely qualifies for self-sustainability to an extent, because we edit code using programs which are Unix processes. We compile them and run them all within this environment. So that system as a whole is quite self-sustaining. It's just the programs within Unix, tend not to be. And at the largest scale, programming and software as a whole is, I think, a self-sustainable system, although it doesn't live in a box on a screen, because the world of computer software is always working on it, changing itself. So self-sustainability seems to be a property that's kind of, it's hard to see how it couldn't be the case at this largest level for software in general. And it's also the case at the large level of Unix files and processes, and also for systems like Lisp and Smalltalk. By contrast, most programming languages and programming systems aren't self-sustainable. So if you want to change how they work, you will have to either shut down a running thing and change it and start it up again, or you'll at least have to switch to a completely different language or programming system to change how it works. So one of the reviewers asked a really good question, and I wanted me to address it, which is, why do I think self-sustainability is such a good thing? Why should you want such a thing? And I think the answer fundamentally is about this dance in programming that we have between commitment and flexibility. So commitment is about removing options, reducing possibilities. It's associated with things like safety and predictability. This sort of thing is appropriate when you know what's going on and your requirements and environment are stable, and you need to be able to make guarantees about things. So an example of this might be a control software for a nuclear power plant. It's got to do one job, and it's got to do it well. And it certainly doesn't need to be able to evolve into a paint program or a game. Flexibility, on the other hand, is the opposite. It's about keeping your options open. It's associated with words like open-ended, dynamic, evolvable. You need flexibility if you're doing work that's ill-specified or exploratory or improvisational, or where your requirements are likely to change. And it's precisely this sort of work that's my cup of tea. I like to try out, prototype new programming ideas, or get rapid feedback on whether a feature feels good to use, and basically just try lots of things out. But even despite my personal bias for flexibility, I think that it seems to me that most of programming would still benefit from more of it, and that commitment is really more of a special case. Don't get me wrong, I think that commitment is fine when you actually decide to have it, but what I really resent is this widespread premature commitment in programming. So a typical programming language commits you to its syntax, its semantics, and its expressive concepts. It really ought to be easier to vary all of these aspects of the programming system to suit the particular subproblem that you happen to be working on. Beyond the syntax of textual languages, I really want the freedom to use the right tool for the job, where that means being able to use the right notation to express any particular part of my program. So maybe I'd rather use a color picker instead of a hex string, or I prefer to express a single line of code containing maths as an actual properly rendered mathematical formula that maybe I could directly edit, instead of what you're normally stuck with, which is some cumbersome ASCII approximation. And if you're really unlucky, your language doesn't let you use operator overloading for something like vector operations, so you have to wrap it in these ugly function calls, add, mul, cross. And it's really bad. A lot of my interest in notational freedom was kindled by Brett Victor's essays, such as this one, Learnable Programming. And in this example, the interface on the right is giving a visualization for the effects of the graphics operations in the code on the left. So it's doing things like changing the coordinate system. It's really nice to just be able to see that instead of having to simulate it and imagine it in your head. And the point is that none of these things are syntaxes. We've got a colored rectangle, maths formulas that have their own special layout rules and font styles. And even the code in the Brett Victor example, it's still living in a rich graphical interface with little annotations. So that still isn't strictly a language or a syntax. It's embedded in a graphical environment. When I delete a file, it goes into the recycle bin. And if I later determine this to be a mistake, I can undo it. I can also, when I'm in the recycle bin, say, please delete this file permanently. And then it will say, oh, do you really want to do this? I like this. I think the commitment should always be explicit and deliberate like this, with things like warnings for these irreversible operations. Even in the case where you're not doing open-ended exploration of features, where you've got a specific product to make with specific requirements, there's still a lot to be gained from flexibility during development before you actually commit in the software that you're going to deploy to users. This is precisely the reason we have debug and release builds. During development, even if the requirements are fairly stable, the way you achieve them might not be very clear to you, so you need to be able to experiment with different implementation approaches. In the games industry, there are often very sophisticated developer tools and hidden cheat consoles that you use during development, and then you're supposed to get rid of these and optimize the final thing for delivery to consumers. This sort of commitment is very important in multiplayer games because you've got these rules and you don't want players to be able to just cheat. But it's precisely that flexibility to cheat that is very important for the development process. Of course, in practice, many games don't bother to actually remove the developer console. They tend to just try to hide it and obscure it. And after about 10 seconds of the game being released, a bunch of hackers have already found it and told everyone about it. But the important point that you have this flexibility during development, but not during deployment, is a sensible idea. But as programmers, we spend a lot of our time in the first step in development. So that's my intuition for why flexibility is, we would benefit from more of it. So I think the fundamental reason why self-sustainability is so good is because at any time you should always be free to reduce your options. But logically, if this is the case, then at any given time, your options, possibilities are either staying the same or reducing. So it's like monotonically decreasing. And so logically, if you work backwards in time, it's only fair if you start out with all the options on the table and you're not prevented from doing anything. So in normal programming, we are committed to prematurely to many, many things, and we have to painstakingly eke out flexibility by adding infrastructure. And this is the sentiment expressed in Greenspun's 10th rule. Whereas with self-sustainable system, this flips it on its head, and you can begin with as few premature commitments as possible and subtract flexibility where you decide that it's appropriate. Another thing that caught my eye in the Kohler paper was that it says one of the things that Kohler's support is mood-specific languages, which are scoped, domain-specific languages in which to express arbitrarily small parts of an application. When I read this was music to my ears. It goes on to say that implementing new syntax and semantics should be as simple as defining a new function or macro in a traditional language. And the paper claims that in Kohler's it really is that simple. So here was a design for a programming environment that took a big step towards a sort of notational freedom and freedom from premature commitments that appeals to me. So you can't blame me too much for thinking, ooh, if only this could be generalized to the case of notations beyond languages and syntaxes. I want to cross out languages and syntax and support mood-specific notations in general. Not limited to syntaxes. It can include mood-specific syntaxes, but not be limited to them, to be able to support these sort of custom notations that I showed a few slides ago. So this Kohler paper, among other things, showed me that the property of self-sustainability could be my ticket to the sort of notational freedom and freedom from pre-commitment that I desire, if it was perhaps suitably generalized. For this, I had a problem. The closest analog to self-sustainability in the world of programming languages is probably something like a self-hosting compiler. So say you've come up with a fancy new language called Fancy, and you want to be able to compile and run it. The first thing you do is you write your compiler in Fancy. You can't run this yet, but what you can do is manually translate this to something like C++ and then compile that. Then you have a runnable compiler for Fancy, but it's written in C++. So if you want to change how it works, you have to use C++. Luckily, you can then use this temporary compiler to compile the code you wrote in step 1. And then at this point, you'll have a self-hosting compiler. You can create the next version of the Fancy language in the current version, and you can keep doing that and work on it by means of itself and forget all about C++, or in my case, JavaScript. This is all well and good for the world of programming languages, but it it doesn't really translate well. It's not at all clear what the analogous process is for building a self-sustainable programming system that's interactive and graphical. The details for building a Cola are all expressed in terms of these sort of batch mode stream transformations and compilation and languages. And it's clearly getting all this from the world of bootstrapping self-hosting compilers. But while that makes sense in the languages world, it doesn't really fit for interactive graphical systems. So my task was to figure out how can we build a system that supports graphical notations and ideally gradually sculpt that into a self-sustainable state. The method that I arrived at takes its cue from what I mentioned earlier about software as a whole being a self-sustaining ecosystem. In the old days, our long-suffering forebears used machine code to write the first assembler and then use that to write the first high-level language and so on from there. So my approach that I converged on was to fast forward a similar process on top of a modern programming system, which is going to have it's going to be vastly richer in terms of features and hardware resources, and importantly, human friendliness compared to the brutally low-level ancestral environment that programming had to emerge from the first time around. So we start from ordinary programming, from a programming system that you feel you are. The idea is it should be a technique you can apply from any starting point. So you pick a programming system that you feel productive in, you're familiar with. I call that the platform. And we just rise through the levels of abstraction similarly to historical computing. We have a low-level assembly language in the substrate. We go through a high-level language later, and all the way up to eventually supporting local notations and getting self-sustainability. I do not have time to go through these steps now, so you should check out the essay if you're interested in the gory details. But I did make this summary slide with examples of what these steps look like for the three examples of Cola, BootstrapLab, and the historical case of computing. I'm afraid I don't have enough time to go through this right now, but I will finish on this slide so that you can look at it during questions. You got your photo. I'll come back to it. What I do have time planned for is to show you that last step, supporting local notations. Let's see if it works. So I'm going to go through again to the structures that in the scene subtree that control the appearance of this rectangle. Collapse some noise here. So I'm going to go to shapes and children, blue shape. So here we have the hex string representing a color. I could use my example from the slides. Suppose I wanted to have a color picker here instead of a hex string. Well, I couldn't get that. That was too ambitious to get to work. But I can show a proof of concept that's an even simpler thing. What if we wanted just to have a color preview here? I mean, we can see what color it is here, but let's say we did a lot more work elsewhere and we can't see the actual shape that it's controlling. What if I wanted to have it so that in the system, when it sees a color property with a hex string, it shows me a preview of what the color is? I have some MASP code here that does exactly that. So it's like a hook that will, when we expand one of these nodes, for every key value entry that it goes through, it will execute MASP code to determine whether to render a custom interface for it. And so briefly, this code will take the key name, see if it's the word color, and if so, it will return a nice colored rectangle with a gray border. So I've got a rectangle on top of another rectangle to get a border. And so if I enable this code to run at the appropriate point, I could do that by setting local notation demo to true. and then I collapse this and open it again, then we get the preview. I open this as well. So we've got the preview with a gray border. And the reason I included a gray border here is because the particular color that we need to insert into it is kind of a runtime value, but a gray border is like a constant value that we can see in the code here, is the A's. And that means that if we go into the code that's rendering this, that contains this constant for the gray border, then we should be able to see that that is also affected by this very code that is implementing a local notation. Children, first child. There. So what's happening here is that this is the code that is implementing the preview of the color, and it's got a color in it which is gray, and this the interface that it implements is able to turn back on itself, on its own code. This is the self-sustainability this is a symptom of self-sustainability that is latent in the system, and you can't do that without that property. That was my backup in case the demo didn't work. Okay, before I close, I thought I'd anticipate some understandable objections. So, isn't this sort of thing just too slow? Well, I have to admit, to be fair, I have done that typical programming language researcher thing where I've shown how to do some ordinary thing like displaying a tree view or the factorial function, but approximately 1 million times slower and with a crude and ugly user interface. But I assure you this is simply because I put zero effort into optimization or into making it look pretty. I've had to focus my time on the thing that I can actually make a contribution to, and that's not optimization. That's just a large established body of work that I could pick a lot of techniques from to improve this. And there's loads of really easy things, basic things that I could do to make it faster. Many of them are covered in the Kohler paper, like caching. I also understand that I understand why having maximal flexibility might be uncomfortable to some, because it's a bit of a risk or a danger. There's that famous story from that legend from the Smalltalk folklore where you can swap the meanings of true and false and brick your system, right? But as I said at the opening demo, I think that the fact that you can do a pointless, dangerous thing like that is a sign that you've got the level of openness that's necessary to be able to do other useful things. And I don't think you can have one of those without the other. So I also touched on this a bit about development versus deployment, where you might not want flexibility in the product. Maybe it's too risky in the product or just inappropriate, but it could still benefit during development. Basically, the more you're exploring different possibilities, whether you're in research or industry, the more that flexibility is clearly appropriate for helping you. So I think the solution to the danger is not to abandon flexibility, but to simply put in warnings and signposts to help orient a person using the system. And this sort of thing is, again, mentioned in the Kohler paper. A related point is that it could be quite complex to understand. While the actual process of building a self-sustainable system is perhaps quite complex, it doesn't need to be difficult to actually use such a system. The Kohler paper covers this, talking about putting in stable points of reference and kind of clearly separating meta-level operations from normal things. The point is you want to have the ability to do something if you decide to, but you can clearly mark it so you don't confuse people. A particularly tough criticism that I don't really have an answer for would come from the direction of Stephen Kell's comparisons of Unix and Smalltalk mindsets. So isn't it just really solipsistic? Doesn't everything have to be invented here? We have to re-implement everything in the system. And for Kohler's that inspired this, I think, I remember in the paper they do talk about integrating the outside world. So I think that I wouldn't say that's definitely the case for Colas, but for my little BootstrapLab, it is a lot more primitive, and so yes, I'm guilty. I guess BootstrapLab is quite solipsistic, but it's a research prototype, so anything could change in the future. So to wrap up, commitment is fine, but not when you didn't sign up for it. Self-sustainability lets you escape from this, and among other things, it gives you the freedom to improve your own programming user interface. The work that inspired me focused on languages and syntax, so I've extended this spirit to interactive graphical systems, and I've showed you what this could look like in BootstrapLab. Thank you very much.
All right, so we have some time for questions, and I will run around with this microphone so that people who are online can hear you. Do you know how to turn this on? Yes.
Oh, thanks for reminding me.
Thank you for your presentation. So it reminded me a bit of Oberon, which was a child of Pascal, which also had a completely self-hosted desktop environment, compiler, runtime, operating system. And there are many parallels. So it was also a bit limited in the flexibility and behavior. And in your case, you have a browser, so you can do a lot of things in a browser, but lots of other things you can't do in a browser. You can never get beyond that.
Do you mean the web browser or the like the tree browser?
The web browser is
web browser.
sort of your hardware in a sense.
Yes, exactly.
You cannot
Yes, hardware.
do certain things in the browser. So I wonder. So first, my two questions: do you think the browser is an appropriate choice for that? That you want to start with flexibility? It seems maybe the convenience of the runtime environment is maybe a large factor, rather than a platform is as flexible as possible. And my second question is, what do you think your primary use case is? Is it for learning programming, something like a successor of Scratch, or do you have other ideas how it could be used?
Yeah, good questions. So the first one was about the browser as like the hardware. Yeah, you're right. I chose the browser platform and JavaScript because it's kind of I'm used to working in it, and it's got these very convenient developer tools. It's also kind of no installation necessary. You've already got one. I like that, but it's. I think you seem to be suggesting that it's important for flexibility to already be present in the hardware, in the platform, but that's not necessary. The important part of the platform is that. Well, I guess the only type of freedom you need to have in the platform is kind of like Turing completeness. It's like a very kind of in principle I could do anything, even if it might be very horrible or cumbersome. So let me think. In the binary world, so this is the case for Cola and historical computing. The natural substrate is binary memory, and in that world, there's kind of a natural code is data thing in a very ugly way, which is just that code is also machine instructions are also bit patterns, and so you can write code and use programs to generate high level programs that way. When you ascend to the level of something like a browser, you still have a language, you still have an ontology of state. So in the browser, it's like, you've got these key value dictionaries, but code actually making things happen is, in the browser at least, is in JavaScript text strings, and so kind of just piggybacking off that would be unacceptable to me, even though strings are part of the state world. It's kind of still in this world of strings, languages, and parsing. So because of that limitation, all you have to do is create a low-level assembly language that kind of naturally fits your state. So in my case, I've got basic dictionary structures representing a small change to a dictionary structure. And so it's kind of just not having the flexibility of being able to generate code is just something you can plug in and patch. So yeah, the platform is chosen for convenience, and not necessarily the flexibility is something you just build on top of it. And the second thing was about what use case. What is this for? It's not a teaching tool. I was scratching my own itch largely. I was inspired by the Kohler paper and wanted to make its approach work, but I felt its ambition and potential was limited by its focus on languages, and maybe it wasn't clear how interactive graphics could be integrated. So I just kind of wanted to kind of fix that and try and build something like a Kohler, but with notational freedom. And I actually didn't end up I haven't done a lot of the steps in there. So I don't describe my thing as a Kohler because it only kind of borrowed the spirit, but not the core concepts. But the point of it is for me to be able to escape my JavaScript text editor and be able to work in a system where I can experiment in a way that I want. And as of yet, I still have not got to that sweet spot where it's actually it's sufficiently pleasant to do work in the system that I don't really need to go back to my text editor in JavaScript anymore. That has been a very stubborn thing that I've kept being most productive in the text editor. But there have been signs of that being able to change, like the tree editor for entering state trees. That's more convenient to use that than to issue commands in the JavaScript console. So it's clear that you could get there eventually, just not there yet.
Hi. You talked a lot in the first half of the talk about deferring commitments until you wanted to make them.
Yes.
Your system currently defers commitments forever. You have all those fun small talk adventure opportunities like swapping the definitions of false and true, or all the other things you can explode yourself in exciting ways.
Yes.
I'm curious, obviously you're not there, but how are you thinking about introducing those commitments and creating a system which enables the kind of experimentation that you're doing without also constantly sort of, holding the knife to your own throat while you're working?
Yeah. Initially, I was thinking, I don't really want to make it. I don't have any commitments I know that I want to make yet. But you're right in the bit about holding the knife to your throat constantly. A recent, I was the code that lets me type in the tree editor and characters appear. That's running in JavaScript, but I was in the process of moving that implementation in system. So when you press a key, it runs some MASP code to change the relevant thing. And I had that working, and I was thinking, actually, I need to change something about how this process works of processing keystrokes. So I used the editor to try and make the change. But as soon as I'd made like the first part of the change and committed it, the code was all different and it was messed up and it stopped working and I stopped being able to type. And I was like, right, yes, I've been burned. So you're right. So that's where, this isn't enough. Yes. Yeah, you need to be able, for this to be practically useful, there needs to be a way to say, I'm going to work on the next version of this thing, but I only want to work on it in one piece once it's all done, not see a partially committed state. So yes, that is necessary. But I don't know, is that a commitment? I don't see that as a commitment. That's just a deferring of a change. That's like a transaction, That's not doing anything irreversible. Yeah. Does that answer your question? Okay.
I have a question about content. So given that you figure out what is it for, right? So you want to target user group, whatever. What about content? So do you plan in such a system to create everything again? Or have you ideas for opening it up again, like reusing other languages, right? If you have a new language, you have to implement everything again.
Yeah.
I was just wondering because the first lively systems if I remember correctly, they used some SVG abstractions, implemented a small morphic in there, and then they had really to implement everything again. The current lively system leverages the document object model, shadow nodes, whatever, so they can just reuse things from other web apps to not have to implement everything again. So what's your answer to the content question to have anything useful in such a system at some point?
Yeah, well, it's a bit of a dilemma because yeah, I was thinking about all this during your talk on the topic, and I don't know what the right answer is. On the one hand, anything that you don't, I don't know, maybe this could be caricatured as kind of control freakery. Anything that you didn't write, you don't control. Or well, the thing is, if you don't have access to the implementation of something, then you can't change it. And in some cases, you have a GitHub repo where you can maybe fork the code yourself. But that mode of changing software is, well, again, it might be a completely different language, so you can't use any of your expertise or custom notations, blah, 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 blah. It's programming as usual. So that's unattractive for that reason. So that's the force that pushes you to say, no, I want to invent it all in here. And so for a lot of the convenient things that I made myself at the beginning in like JavaScript, like the HTML column in the middle for the state view, in the paper I reified this. I called it debt because it's clear when you're doing this. It's like, well, this will be a really neat thing to be able to affect from within the system, but it lives in JavaScript and the system can't see it. So at some point, I'm going to have to re-implement this inside the system, and that's more work. But on the other hand, yeah, there's something really stupid about having to. You want to make things better, so now you just have to. All the work that everyone's ever done, writing every graphics library, every library for compression, everything, all the work that other programmers have done, you now have to redo, or you have to recruit some unfortunate community of users or grad students or something to then force them to do it. This is clearly wrong, and there has to be some way to play nice with outside things and to bring them in. And the Cola paper has it talks about being able to see things that are from a foreign environment and kind of interact with them or make use of them. And yeah, you have to have some way of doing that. But I don't know what it's going to be with mine.
All right. Well, thank you very much. Let's applaud the.